All right, welcome everybody to RMI's workshop titled Low Embodied Carbon, a deep dive on specifications. This is part of a workshop series that we've been hosting over the past year, targeted at state DOT and other agencies, local and tribal across the US, on the topic of implementing low embodied carbon concrete mixes. Today I'm joined by a great panel and speaker roster. From RMI, we have Audrey Remfer and Satyam Maharaj. From the University of Toronto, we have Douglas Hooton. And then we're joined by DOT staff from 3 agencies. From Oregon DOT, we have David Dobson. From New Jersey DOT, we have Ryan Ratman. And from Caltrans, we have Jackie Wong and Joe. So thank you all for joining for this session. A quick bit of background on this workshop series if this is your first time attending. Our objective here is to shape DOT action to address embodied emissions of concrete. We're really looking to build collective understanding of some of the key barriers to adoption of low carbon concrete and identify solutions together. We've honed in on the specification barriers to low carbon concrete, and that's the focus of this workshop. And then overall, we're trying to build confidence in emerging blended cements, such as LC3 and other 1T blended cements that are coming into the market today. The past workshops that we've had, last year we had 2 workshops, one in June that was focused on EPDs and emerging buy clean programs. We had a second workshop in August that was looking at the application of limestone calcined clay cement, or LC3, at DOTs. And then today we're going to be doing a deep dive on specifications and how specifications can be used to unlock low carbon mix design. So today's agenda, we're looking to align on pain points and next steps for US DOTs to adjust specifications to unlock lower carbon concrete mix design. And our outline is, we'll have a brief introduction from Satyam to show some analysis that RMI has done to quantify the carbon reduction benefits of adjusting certain specification criteria. Then we'll hear from Doug, who will present on performance-based specifications, sort of the long-term vision for how well-designed specifications can enable flexibility and carbon-optimized mixes. And then we'll have a discussion with DOT staff just to hear on some of their experiences and current work on this topic. And we'll wrap up the session to hear from you. We'll have some live polling and identify some focus areas for next steps on this topic. So with that, I'll pass it to Satyam to walk us through some of RMI's recent analysis.
Thanks, Anish, for that introduction, and welcome again to everyone joining us. It's my privilege today to take you through this analysis that RMI has done on the current pavement specifications that state DOTs are following. Next slide. So what did we do? RMI reviewed the DOT specifications across 15 states with a focus on concrete pavement application. We use this as a basis to find key takeaways and how these specs can be updated going forward to enable low carbon concrete mixes. Next slide. We found that most of the 15 states we assessed continue to have overly prescriptive minimum cement limits in their specifications. The map shows the states we've assessed. States highlighted in blue all have minimum cement requirements, while those in cream do not have minimum cement limits. Next slide. Further to this, we found that different states are achieving similar strength requirements with varying minimum cement requirements. This graph shows a comparison of the strength requirements on the y-axis versus the minimum cement requirements on the x-axis. For example, Florida and New York have the same minimum strength requirement of 3,000 psi. However, Florida has a minimum cement requirement of 470 pounds per cubic yard, while New York has a minimum of 605 pounds per cubic yard. What does this mean for the potential emissions of these states? That's what we at RMI are trying to find out. We conducted an analysis to find the potential greenhouse gas emissions of these states. We did this by gathering state DOT specifications on minimum cement and strength requirements and maximum allowable fly ash content. ACI design guidelines were then used to develop typical mixed designs for 1 cubic meter of ordinary Portland cement concrete per state. Following on from this, a greenhouse gas emissions calculation based on the NRMCA emissions benchmark data was developed. Next slide. The results from this analysis show that when compared to typical OPC emissions, current specifications from state DOTs have the potential to reduce pavement emissions by up to 37%. The graph shows the potential state DOTs have to reduce their pavement emissions by utilizing their current specifications. The x-axis shows the differing states, while the y-axis shows the greenhouse gas emissions in terms of kilograms of carbon dioxide equivalent per cubic meter of concrete. Michigan has the biggest reduction potential due to their specification allowing for the implementation of up to 40% fly ash as a supplemental cementitious material. In the case of our earlier example of Florida and New York, we can see that Florida has a lower potential specification emission of 263 kilograms of carbon dioxide equivalent per cubic meter of concrete compared to 301 for New York. Both have the same minimum required strength, but Florida has a lower minimum required cement content. Next slide. So how can we use this data to further reduce our greenhouse gas emissions? We see a graph with the same axes as before, states on the x, and kilograms of carbon dioxide equivalent per cubic meter of concrete on the y. Specification emissions can be reduced by up to 33% by making the switch to a 50% fly ash and slag blend. Next slide. What's next? DOTs should look at setting carbon intensity and emissions reduction targets. Set limits on carbon dioxide emissions per unit of concrete produced. Adjust minimum cement requirements to allow for the full utilization of maximum SCM limits. Further, the use of SCMs should be optimized by transitioning to mixes with a 40% fly ash content and a 50% fly ash and slag blend. Prioritize the use of emerging SCMs and blended cements such as LC3. And with that, I'll hand you over to Professor Hooton for his section of today's presentation. Thank you.
One of the get rid of the side thing too. Where we want to go, and it was already mentioned in the previous slides, we want to use less clinker in cement. We want to use less cement in concrete. We want to use less concrete in construction by optimizing. It's a little tougher for pavements, but for buildings, there's ways of optimizing design to use less concrete. And so, as was mentioned, use blended cements, including 1L cements, or replace clinker with supplementary cementitious materials at the concrete plant. You can use less cementitious materials by optimizing aggregate gradations and lowering the cement content as a result. And we can optimize designs. So you can use alternative materials, as was mentioned. So how do we specify these things without being prescriptive and preventing, which may prevent the adoption of new technologies? Okay, so what's the difference between a prescriptive spec and a performance spec? Generally, a prescriptive spec, which is the traditional, most specs are prescriptive to some extent, other than maybe specifying strength as a property. So it places the material into a defined category, and often there's chemical limits or physical property limits, implies properties to the purchaser without stating them explicitly. For example, if you say class F ash, people assume it mitigates ASR. It sets spec limits that are rigid and can misrepresent a material, and implies that all the materials in that category are exactly the same. Whereas a performance spec measures, reports, and in some cases limits properties, but relates the material's properties to performance outcomes. Materials are categorized based on expected performance. For example, in ASTM 1157, type HS means high sulfate resistance, MS means moderate sulfate resistance, so performance by cement type. And the lack of chemical or the not inclusion chemical or compositional limits allows multiple materials to be specified as long as they meet the same performance requirement. So some of the barriers, we need to know how to use performance test methods and specifications. For example, ASTM 1157 was designed as a performance specification for cements in 1992, over 30 years ago, but very few states have adopted it. I think maybe 7. It is included, it's mentioned in the ACI building code and other doc code documents, but it's rarely invoked. As a result, very few producers make it because there's no demand for it. And users say they want performance, for some reason still wants to know what's in the cement. And that's the big difference between 1157 and C150 or M85 and AASHTO. There's a few prescriptive limits on compositional requirements and chemical limits, but so maybe it's not the performance people are looking for, or they don't quite trust the performance that's there. A lot of the quality control, quality assurance is based on historic legacy prescriptive approaches, and adding performance tests presents challenges by measuring properties that specifiers, engineers, and architects may not fully comprehend. Because everybody's a cook, as shows in the cartoon on the right. So if we want to move to performance specs, we require performance-based test methods. Currently, we rely mainly on prescriptive tests. Some are nearly 100 years old. Tests need to be practical and fast, or relatively fast. And some of the barrier to adoption is slow. Between time initiating a test and getting it adopted in standards, we need to correlate with field performance, and that takes time. And we need precision on the test method and reproducibility. And reproducibility is a key element here. You need consistent results for performance specifications. You can live with not knowing what the material is if it's demonstrated to perform consistently, and if the performance can be substantiated by testing. And then so sampling and uniformity testing becomes a more important part of that story to make sure that it's consistently performing. Now, I chair the Canadian Standards Committee on Concrete and Concrete Test Methods, and we've had performance specifications since 2009. It requires concrete to either be specified completely by performance or by prescription. We used to have what's called a hybrid common method, which is what a lot of occurs in a lot of the US specifications. It's a mix of prescription and performance. And unfortunately, this confuses responsibility. Who's responsible for what? And I'll explain that a bit more. As a result, it's been adopted in the building code since 2010 in Canada. And almost all specs have now become performance-based because the prescription implies that if an owner or specifier takes on the responsibilities for performance, if they've prescribed it. So if you prescribe something, then you own it. And we've been cleaning this up in subsequent editions. The newest one will come out a little later this year to improve the details and guidance related to that and how we set limits and putting new performance test methods and limits. Now, initially, as I said, there was pushback from designers and specifiers when we introduced this. They said, "Oh, no, we don't want. If we say, minimum cement content, then we still want you to perform." But what we said is the way that we designed this in the specification is if the owner or designer adds prescriptive limits, it's deemed to be performance, and they become responsible for that performance. And nobody wanted that responsibility, so all of a sudden, people were a little more amenable to change because nobody wants to take on the responsibility for the performance. Prescribe the performance, test it to see if it meets your performance, and accept it that way. And so what do we mean? In the Canadian standard, we define performance requirements when the owner requires the concrete supplier to assume responsibility for performance of concrete as delivered, and the contractor to assume responsibility for the concrete in place. It's a method of specifying a construction product with the final outcome and given in mandatory language in manner that the performance requirements can be measured by accepted industry standards and methods. And the processes, materials, and activities by the contractors, manufacturers, and suppliers are then left to their discretion. So just let them work together to come up with the final outcome that meets the performance. So the responsibilities of all the parties need to be clearly defined in the contract documents. And we define those in the Canadian standard for the owner, the contractor, the supplier, and the testing companies. And you have to have a system of owner, specifier, contractor, and supplier producers quality assessment. And of course, all this relies on good communication. So any deficiencies happen, they're reported immediately, and change orders are made to make sure it doesn't continue. Now, this is a really busy table, and I don't expect you to all read it. And so we just look at the top, which is the performance option. It basically says the owner shall specify, the contractor shall do, and then the supplier shall. And so basically, you say what the requirements are for that product, and it can be anything the owner wants. It can be strength at certain ages. It can be durability criteria, class of exposure, any other volume stability, architectural requirements, sustainability issues, additional owner performance pre-qualification or verification, quality management requirements, any certification for the suppliers, and any other properties that the owner wants, but they have to be measurable. So I'm not going to go into the rest of that table because there isn't time. And of course, like 318 and other specifications, the Canadian standard uses a table of exposure classifications to set that performance for different exposure requirements in terms of the materials, properties, and curing. And we define those responsibilities in that table, but we also have a large annex to the standard, which goes into a lot more detail about those responsibilities. And we also have standard practices for qualification testing of concrete and acceptance testing of concrete during construction. So that's clearly what's being tested, when, and what the requirements are. Now, typically, in most specifications, concrete's accepted based on the fresh property slump or slump flow and air. And in many cases, the only hardened property specified is the 28-day strength. But that's not an adequate metric for performance. Often construction schedules are controlled by early age strength, which then puts requirements on perhaps cement content and water cement ratio to get those early age strengths, because people talk about 28 days, but they often want 1 day strengths or 3 day, especially in vertical construction. Concretes with high SEM levels typically develop their ultimate properties at later ages. And so we typically, in the Canadian standard, we set limits at 56 and 91 days, as opposed to the 28 days when there's durability requirements. And also when people talk about low early strengthening of high SCM mixtures, if you only cast cylinders, like a 6x12 cylinder or 4x8 cylinder, and store it at a constant temperature in a lab, you're underestimating that concrete development, this development of properties in that concrete, because SCM concretes containing SCMs are far more thermally sensitive. With the heat of hydration builds up, the temperature rises, they accelerate a lot faster than a Portland cement mix. So if you keep them at a standard 73 Fahrenheit in a curing room, you're not seeing that potential development. So the in-place development of strength is often much higher than is predicted by cylinder tests. So what are the performance attributes? Other than strength, for durability, we want something that indicates the resistance to ingress of aggressive fluids, whether it's chlorides, sulfates, or whatever, or acids. The ASTM C1202 or AASHTO 277 or a bulk resistivity test would provide some index of that resistance. And those are being adopted. The Canadian standard uses rapid chloride permeability limits. Now we're introducing bulk resistivity limits as performance measures for durability requirements. And of course, you need tests to qualify the aggregates to make sure there isn't going to be an alkali silica reaction, or if you are going to use reactive aggregates to determine the required mitigation measures. And then, of course, you have specific exposure requirements for sulfate resistance, if it's applicable, freezing and thawing, if you're in that environment. And of course, related to that is de-ice or salt scaling. So you have applicable test methods that come in and requirements based on the applicable exposure. And this can work. Performance specs can work. We've been using it quite successfully. We haven't had a lot of problems. In fact, the number of problems have gone down since we adopted performance specs in Canada, provided everybody's on board. Everybody has to be involved in the process. They allow for innovation in the supply of concrete because it means that you can supply, concrete producer can supply different materials in proportions as long as it meets the owner's performance requirements. And this allows potentially more environmentally friendly concrete materials, in other words, lower carbon concrete, with that option, or with those flexibility. And of course, performance means more than acceptance of concrete at the end of the truck chute. I worked on the NRMCA P2P with Ken Hover many years ago, a project to try and get performance, but really that ends at the chute for the NRMCA. It really means to the owner, in-place performance of the structure. So everybody has to work together as a team to meet those specifications. So the risks and responsibilities are different than in performance specs. So there's a learning curve, but it's been was a very rapid curve actually, because contractors always know how to make money. Okay, now there is stuff going on with AASHTO. There's the R101, the Performance Engineering Pavement Mixtures project, which I'm sure you're all well aware of. And they're focusing on what are the parameters to measure in that as well. So there are things going on within the highway groups in the US. And of course, related to that is defining things that matter. Again, transport properties, aggregate stability, in other words, ASR, other properties, strength, and of course, the same things I've already mentioned, and volume change in terms of shrinkage, and of course, workability of the fresh concrete. And of course, it depends on where you are. In this little map of North America there in the bottom corner shows, of course, from zones in terms of climate zones. There's climate, like in other words, freezing zones, and then there's marine zones as well, that you worry about different things, so that the map's been divided up an area where you have different exposure concerns. Because one of the things is that time is running out. Global warming is increasing. We've seen increased in Canada. We had huge forest fires right across that. If it went down into the US, the smoke and smog. There's been droughts. There have been flooding. There's all kinds of extreme 100-year events are happening about every 5 or 6 years now, and it's accelerating. So we need to do things quickly to meet the industry, and the governments are pushing for 2030 goals to partially reduce greenhouse gas emissions and global warming, and concrete's part of that story. And so what are the low-hanging fruit? You can do things that are allowed now using Portland limestone cements, 1L cements, which results in about a 10% CO2 reduction over plain Portland cement. Increased use of SEMs, and the CO2 reductions proportional to the replacement level. And they also result in better durability in most cases to chloride ingress, sulfates, ASR, and improves resistance to thermal cracking. Now, there may be some really strength issues, as I mentioned, but you can design around that. Optimizing aggregate gradations. The paving industry has done a pretty good job in most places, allowing optimized total aggregate gradations, because it reduces volume change and curling and shrinkage for pavements, but it's not done across the board at ready mix. We typically have a fine aggregate spec, a coarse aggregate spec, and you can save by optimized aggregate gradations between 5 and 15% of cement, and increase the aggregate and improve the concrete properties in terms of shrinkage and permeability at the same time. But that requires some capital investment and more bins and all that. These things are already allowed in the building code and in the various specifications, and they can be done simultaneously to bring down a cumulative reduction in global warming potential. And as an example, this is just, if you use a type 1 cement, you've got 91% clinker in the binder. If you go to 1L, you're about 81. 1L with 25 ash, you're about 61, and 50% slag with 1L, you're down around 41% of the CO2 emissions or percent clinker, which then, and since clinker is 90% of the CO2 emissions from concrete, the clinker content of concrete, that means you're having a significant impact of reducing CO2 emissions. And 595, ASTM 595 and the AASHTO equivalent allow 1L cements. SCMs are allowed in most concretes, although sometimes limits. C94 mixed design allows optimum total aggregate gradations. Over 50% of the cement in the US as of October last year was Portland limestone cement, and it's almost 100% in Canada. All the concretes contain, most concretes, about 90% contain some level of SCMs, although sometimes limited by prescriptive specs. And so what can be done now? Don't specify minimum cement contents. Specify the performance you're looking for. I mean, a lot of these minimum cement contents are legacy from back when we didn't know as much. And we didn't have chemical admixtures and other things that can be used now to optimize concretes. Don't restrict the use of SCM levels. Allow them to be used to meet the performance requirements. Specify the performance you want, whether it's setting times, early strength, or de-ice or salt scaling resistance or whatever. Specify what's needed for that concrete application. And with that, I will quit because I think Anish wants me to finish. So there you are. Thanks. And I'll stop sharing.
Thanks a lot, Doug. That was a really good sort of jump into performance-based specifications, which really are the vision for how we can enable highly flexible, optimized, low greenhouse gas emissions mixes. But I like that you ended with the low-hanging fruit and things you can do today, and really driving home the points about getting rid of minimum cement limits, expanding the use of SCMs. So, with that in consideration, we're going to hear now from an esteemed panel of staff from a range of DOTs across the country who are really on the front lines of making this happen. So, if you all want to come onto video and we can get started. Doug, I did see a question in the Q&A for you on your talk. So if you're able to respond to that, that would be helpful.
Okay. Yeah, I'm not clear on the question. Has Canada seen a consolidation of cement manufacturers after adopting performance specs? We expect these standards would cause less capable producers to exit. Well, we only have this pretty much the same big players in Canada as I think there's 7 producers of cement, different companies in Canada. There's the Lafarge Holcim, there's the Heidelberg, there's St. Mary's, there's Ashgrove, and a few others. So we haven't seen any reduction in the number of players with performance specs.
Great, good to know. Awesome. Well, maybe to kick off this discussion, I would just ask each of our panelists to give a little bit of an introduction to some recent efforts underway at your agency to reduce the environmental impact of concrete materials. And we have a few slides that we can thumb through as folks answer. I think Oregon DOT.
Looks like mine.
Up first. Go ahead, David.
Yeah, so David Dobson with Oregon Department of Transportation. I'm the structural materials engineer. So I guess I'll start talking about SCMs. Doug brought that up quite a bit. We've been encouraging the use of SCMs for many years. We go up to the ACI limits currently, ACI 301. We've added some new SCMs to our QPL, our qualified product list in recent years, most notably natural pozzolans. We've also looked into ground glass pozzolans and reclaimed fly ash coming out of Canada as well. We've always had a focus on durability. Our high performance concrete, that's a performance-based specification focused on shrinkage, durability, permeability. Internal cure is one technology we've been going after, especially for our bridge decks, to increase the durability of concrete, make it last longer, replace it less often. And then most recently, we have a new House Bill 4139, which focused on EPD collection. Tied to that, we have a new sustainability engineer and climate office. It's all focused on sustainable materials and lowering our greenhouse gas emissions. So thank you.
Thanks, David. Maybe I'll pass it to Ryan to talk a little bit about New Jersey.
Sure. My name's Ryan Rathbun. I'm a geologist at Bureau of Materials here, and I oversee our cement and aggregate labs. One of the more recent things we did, and going to the term of low-hanging fruit, was the adoption of the Type 1L blended cement. We were approached by industry back in 2018. We had always been aware of it, but we weren't really aware of the adoption of the testing under the C595 standard, which we already had on the books. So based on the adoption by AASHTO and ASTM of accepting Type 1L as part of their standard, it was really a simple specification change for us, because as long as your product meets the 595 standard and it compares favorably to a Type 1-2 cement, and testing obviously had to bear that out, it was a simple adoption for us. Many of our contractors were pretty happy with the performance of it. We didn't really require too many pilot projects or anything. And that's based on the nature of the product. It's, if you ask any mix designer, they'll tell you it's a 1-to-1 replacement ratio. You get, your early strengths aren't as high maybe, but you're still going to meet standard. And over a long term, you're going to see higher strength potentially. And so all of that combined with the 10% reduction in energy inputs made it a really easy to swallow type of specification change. And we've been using 1L on large projects since 2021. Almost all of the market now, at least from the big suppliers, has gone that way. I can't really speak too much to the precast market, but I'm speaking to all the batch ready mix plants. It's quite abundant here in our market in New Jersey.
Thanks, Ryan. Maybe I'll pass it to Caltrans to speak a little bit about their active sustainability strategies.
So I think some of these are a little older, but thought it would be worth mentioning here. But in the 1990s, we started up our product evaluation program, and that includes things like new product evaluation as well as authorized materials lists. 2000s, we got a maximum Portland cement and minimum SCM usage limits. 2019, we've got EPDs and other materials for other materials like steel. In 2020, recycled concrete aggregates, that's our non-standard special provisions, allowing the use of recycled concrete aggregates in our mixes. Blended SCMs, including PLC and ternary cements, came out in 2021, and it's anticipated in 2024 that we adopt a blended SCM into our specification. And I think there might be another slide, I don't know, after this one. These are the more recent efforts. We've got our pavement materials partnering committee. I'm not going to mention all these, but our PMPC with industry and Caltrans, and the first one there is the sustainability and performance-based concrete specifications. That's what we're calling our roadmap for concrete. The effort really seeks to develop performance-based specifications to help us quantify and reduce greenhouse gas emissions. But we all obviously want to maintain long-term durability of the concrete as well. That's still in its draft form. It has not been approved by management yet, but it's moving in that direction. Another thing here on ongoing research, we have use of alternative SCMs, and we're in the process of identifying and testing ASCMs that are abundantly available in California. And that includes calcined clay, natural pozzolans, biochar, glass powder, those sorts of things. And then other effort didn't really fall under either one of these two things. We're talking about green CMU, concrete masonry units, based on EPDs. So in California, the industry has already developed EPDs for their CMUs. And so, but there's no way for Caltrans to collect those and see what their EPDs are. So we're looking at putting in our spec, hey, you just need to give us those EPDs and we'll monitor them. And then that's really the first step for the CMUs. And they've already done that, but we need to be able to collect those.
Great. Thanks for those overviews of the current efforts underway. Since this workshop has been focused on spec changes and adjusting specs, I thought a good question to ask you all was, giving the sense of how you actually update a specification. And I know, David, you had put together a slide on what the spec update process is in Oregon. So I wonder if you could walk us through that to give folks a sense of how it works.
Sure. It's pretty simple. ODOT is a pretty streamlined state as far as our specifications go. It starts with a research review. A lot of our research runs through our research section and eventually to Oregon State University. We're really fortunate to have such a great group of researchers there with Jason Weiss and Dr. Eidecker as well. So when we look through that research, eventually produce a specification change request, which is reviewed by the materials engineer or the technical resource. We also have a qualified products list. Most states utilize either a QPL or APL for the majority of our materials, cement, pozzolans, SCMs, admixtures. Those are all on our QPL. So if we're looking at adding a new QPL material, that's going to go through our qualified products list coordinator. All these spec change requests get a period of industry review. So that's typically our OCAPA, Oregon Concrete and Aggregate Producers Association, and our local AGC. So it's pretty streamlined. For example, adding natural pozzolans, we reviewed the research. There was a developed ASTM for the approval of of natural pozzolans. So we added that review category to our qualified products list, which allowed manufacturers of natural pozzolans to submit their materials for inclusion on the QPL. And so we have one or two natural pozzolans that have been added to the QPL recently.
Thanks. Jackie, I wonder, in response to that, if you could speak on how Caltrans's specification update process works, and maybe speak a little bit about how PLC was approved across the state.
I really wish we could sum it up in 3 boxes with 2 arrows. Exactly. I guess just to oversimplify it, because it is a little complex. I from my perspective, at least, it's almost like a lot of our spec changes. It feels like a crowdsourcing type of methodology, I guess. But it really, anyone can initiate spec changes, and then really it kind of ends up in a committee dedicated to that particular section, I guess. And so I like to just reiterate, Caltrans is 22,000 employees. We've got hundreds of different divisions and subdivisions, and they own different sections of our spec book, which is very north of 1,000 pages now. And so whenever there is a specification change, generally it goes through a committee, and there's different stakeholders. And so that's kind of the general basis of it. And then specifications that really do impact industry that are a little bit more significant in nature. Caltrans has a committee with the industry, so the industry has, association representatives representing the cement, ready mix industries, and then they're working with another Caltrans set of representatives that are representing pavements, materials, construction. And so together, when I say crowdsourcing, it's, hey, here's something that could use improvement. It gets on a bin list, and we work through that with our industry group to figure out, hey, how can we improve that? And so that's kind of the consensus basis where we make spec changes through especially material specifications that will impact industry. And so like PLC specifically, I think there was a lot of support on all sides of how do we adopt this. And really it started with kind of just the literature review and figuring out what the gaps that were there. It wasn't like we could just snap the finger and put it into the specs. And so there were some research gaps that existed. And so even in that sense, we had about 10 steps we had to get through before we could do the spec changes that we were hoping to do. So with that, it was a joint Caltrans industry, reviewing the research and then taking that research into what the specification changes would look like. And even after, some of the major stakeholders had reached an agreement, we still in Caltrans had to go after another probably 24 stakeholders to get the concurrences, because when we changed the material spec, we went across the board. So we were changing like concrete pipe, we were changing minor concrete, where we use cement and soil stabilization. So we were trying to adopt that wholesale all across the board. And so we had to go to these individual stakeholders to make sure and make our case like, hey, we've done the research, this material adoption to allow 1Ls is going to be okay for whatever your use case was. And so that's what took probably 4 to 5 years from research to specification change, for us at least.
Thanks. And we've been talking about PLC, we've been talking about blended cements, and I think it'd be useful for folks to understand the difference in how adopting those materials might be. And Jackie, I know you had mentioned that Caltrans is experience with PLC is not necessarily one that could be immediately replicated to 1T. Do you have any thoughts on how the emerging blended cements in the 1T category could be adopted in a more streamlined fashion?
Yeah, so I guess for California, and every state's going to have a different, context, right? Like say context sensitive. So California, there's like a couple feet of snow, a couple hours to the north, but then there's probably still people at the beach today, right? In January. And so being very cognizant of the different conditions that we had. I think Doug talked about just performance means something different in different places. And so for us, it felt there were so many impacted stakeholders to keep into account, right? And so different durability concerns, different locations. We split our state up across into 12 districts. And so making sure all the different districts that, have to implement the specification were on board. And so for us, it would have been nice, we did at the time when we were considering PLC, at that time we were told there was at least 30 other states that had already adopted. And so it was like, okay, what's the literature review say? What questions have already been answered so that we could just, what's the delta, and then move on from there. So I guess if we're looking for advice, I would say like we shouldn't, as states work alone. There's a lot of similar durability issues or concerns or local material issues that we all kind of have in common. And so, doing the literature review, knowing where we all are, and then taking the next step so that we don't have to recreate any of the work that's already been done. So from that perspective, it can be different in different states. So, but we were just grateful that there was so much research done already by the time we were ready to look into adoption. Great.
Yeah, I wanted to pass a similar question to Ryan. I know in New Jersey, you explained earlier that the introduction of PLC was pretty efficient, almost sort of like a one-to-one swap without making detailed adjustments to like mixed design specifications. But how do you think that process is going to be different as you start to incorporate new blended cements?
So the answer is it's going to be a little more difficult for two reasons. One is our specs don't allow a ternary blended cement outright. So that's just a grammatical change. But when you get down to it, so the PLC, that's a binary cement. It's got the limestone already in it. The ternary cement has some type of SCM, or it's volcanic ash or some other mineral that's essentially acting as a pozzolan. In the Lehigh Valley over in Pennsylvania, they have a ternary cement that has slag in it. But it's essentially, it's three components. And what that does is it changes some of the design requirements. For the biggest issue I think we're having is where PLC was a 1-to-1 replacement. On paper, 1T is not. And that's due to, I think it has a lot to do with the water requirements. The 1Ts have maybe a finer gradation, especially on the really fine scale. And they're going to require, they're not going to meet the minimum water requirements that we're finding with Class A, Class B. And where it's really going to be difficult is when we get into the high performance concretes. A lot of our high performance concretes have a prescriptive, not just the minimum cement content, but we have a prescripted pozzolan content, whether it's a slag or a fly ash, and that's driven by the ASR reactivity of the aggregates. So if you're going to use a potentially ASR reactive aggregate, you need 15% by weight fly ash or 20% by weight slag. And you have to balance that with now a 1T cement that doesn't meet your established water to cement ratio. And it also has a pozzolan in it. So you have to balance the equation with what does the specification already require in the way of ASR remediation, and what kind of pozzolan is already blended into the cement that you want to use. So there's it's not as straightforward. There's more balancing that needs to be resolved. And but again, with PLC, the research was already done. So that's why it was a relatively quick adoption for that specification change. The 1T, we have Rutgers doing some research right now. And they're going to work on, maybe we adjust the water cement ratio for an HPC if you're using a 1T cement, and certain exceptions that would allow the use of 1T. We're just not going to treat it as a traditional type 1-2 cement.
Great, that's really helpful. And maybe a follow-up question to that is, so 1T, we're talking about blended cements where SCMs or other materials are essentially pre-blended and you're purchasing that cement versus that being mixed on site. But I know you've been trying to address a shortage of fly ash across the country, and specifically New Jersey, and you've been looking at a lot of other SCMs to apply into mixes. And you'd mentioned that you were having some challenges with calcined clay. And so, thinking about the blended cements that we're seeing as opportunities, which include calcined clay, and then your experience with trying to apply metakaolin or calcined clay in a mix. Could you speak a little bit about what the barriers were to applying that material?
The barriers were largely logistical. We had someone mentioned earlier the C618. There's a category of natural pozzolan. So the testing is already established. We're close to the good anthracite coal here, so we're kind of blessed for years as to having that low carbon coal ash that made for a good SCM. But as the plants went away, we're looking for new sources. So the calcined clay I know it's really big in the southeast of the US. We had different companies approach us, and we were able to test it. It meets the C618. But then what happened was COVID, everything goes up in price, and the supplier's main access to market here was via the rail. So once a lot of the rail freight pricing went up, it wasn't worth their time to bring it to our market. So we have an approved metakaolin or calcined clays that we would love to see in our market, but it's cost prohibitive for these suppliers. So what's been happening is, I think Dave mentioned reclaimed ash. We have 2 sources of reclaimed coal ash. They estimate they have about a 15 to 20-year supply. There are countries in the world still using coal. So we're getting coal ash from, India and Southeast Asia. They're bringing it to our market. But that's not sustainable in the long term. So we're looking for other sources. We're looking at ground glass. We're looking at other things that can essentially act as a pozzolan for concrete production.
Awesome, thanks for that. I know we're nearing the end of our time together, so I just have a couple of more questions for folks, more on the topic of performance-based specifications and how we can move towards the model that Doug presented on. So a question for you, David, is could you describe some of the performance testing oriented specs that ODOT currently uses? And then what's preventing you from going to a full performance-based approach?
Sure, I could use the example of our high performance concrete for that. We have a prescriptive specification for HPC concrete. We also have an option for almost completely performance-based, where we test for permeability and shrinkage. Yeah, here we go. Durability testing, right? And I think Doug alluded to this in his presentation, and that the tools for full performance testing and durability testing are there, right? Formation factor, resistivity, permeability, and plastic properties like the super air meter are coming on board, and some suppliers have started to adopt those. They have those abilities, but not all of our suppliers would be able to incorporate those performance technologies into their mixed design process. So we're still relying on certain prescriptive specifications, which I guess means we have some hybrid specs, which Doug cautioned against. Things like the maximum water cement ratio, we still have that as a means to reduce shrinkage, but we've gotten rid of minimum cementitious contents many years ago, just purely focused on strength. And I, hopefully over time we'll continue to include options for performance specifications, and suppliers can adopt those at their own pace, especially as we start collecting EPDs. We're not to the point of thresholding yet on greenhouse gas emissions, but that is likely coming in the future. So once we get to that point, and concrete suppliers want to make greener and greener concrete, they can do that with performance specifications that hopefully we can just slowly incorporate those as there's more comfort in the industry. So I think those tools are there.
Great. And last question for the Caltrans folks. You mentioned your road mapping process to get to performance-based specs. I wonder if you could walk through that a little bit and provide a timeline. I know there was a slide on that, so you could just give us some.
Yeah, this slide here is kind of a one-page breakdown of our draft roadmap. Once again, it's a draft, but essentially communication is key here, and close collaboration with industry and Caltrans subdivisions. I mean, as Jackie mentioned, there's a lot of different subdivisions that have to buy off on this because concrete is pretty much everywhere. And pilot studies might be necessary as well. and we need to align with our ongoing research as well as PMPC efforts. So some of the stuff we're looking at here is identifying and removing unnecessary prescriptive requirements when it's applicable, establishing baseline data for engineering properties and as well as environmental characteristics. Selecting requirements that secure desired performance, but keeping our sustainability goals in mind, conducting studies and development of specifications, as well as sampling and testing procedures, incorporating EPDs. And then some of the most important stuff is actually the implementation plan, because we're so big that people are going to need training and certifications to maybe run some of the testing that's required, update our guidance documents. I mean, there's hundreds, I don't know, I'm guessing hundreds of manuals within Caltrans that address concrete in one way or another. And obviously update our specifications and roll out those specs. So here's a EPD LCA timeline that we have developed, also a draft, but it starts off with EPD collections for concrete and asphalt this year, and then it ends in 2030. At least this shows that it ends in 2030. We need to make it clear that these EPDs and LCA, yeah, it's useful to do, but it also needs to be in conjunction with our Caltrans roadmap for concrete sustainability and performance based. They kind of work hand in hand. It's not this isn't a fast process, and this document here, this timeline is for both concrete and asphalt. We don't want to create an unnecessary war between concrete and asphalt industries. They both have their pros and cons. I think that's it there.
Great. Thanks a lot. And I know we're slightly over time, so I don't want to keep folks any longer. And I hope you learn something from our panelists and from our speaker on performance-based specifications. So thanks for joining. I know we had promised some interactive polling, but our panel discussion was just too good to pass up. So we'll be following up via email with a survey with some of those questions. And really, we're trying to crowdsource information from this group. And so we'll share back the results from that survey. So we hope you don't ignore it when we send it to you. But thank you for attending, and we'll be continuing to host these workshops throughout the spring. So we look forward to our next session. And a special thank you to our panelists and speaker for joining us today. So really appreciate everyone's time.
Yep, thank you.
Thanks all. Have a good day.
Thank you.
Thank you.